Okay, thank you for joining us this afternoon for our presentation on the role of flash chromatography in natural product research. Today's presentation will be presented by Jack Silver. And before we get started, I'd like to just take care of a few housekeeping items. You notice on your browser you have a chat feature in the upper right-hand corner. Any questions that you may have during the presentation, please use this chat feature to submit those. And at the end of the presentation, we will answer all the questions in the order that they were received. And with that, I'm going to turn the presentation over to Jack. And Jack, when you're ready.
I am. Our agenda for this presentation is we're going to discuss some initial steps for screening natural products. We're going to talk about the different columns that one can use for screening on an automated flash system. We're going to talk about a technique called Wide Polarity Range Chromatography that I find very useful for automated flash chromatography with some examples. And then we shall have a conclusion. The initial steps prior to extraction, this is really meant for people who are new to natural products research. Those that have been working in the field probably use these techniques already, but before doing any sort of purification, spend a little bit of time looking at the genus and species in the literature and see what compounds have been isolated already. You can then generate a list of known compounds and existing purification method. I mentioned the family as well because I've had some fairly good luck at searching at that level and finding compounds that are generally produced and known for the family. This enables faster screening of known compounds and lets you move on to the next project more quickly. Some good sources include the American Chemical Society journals, Science Direct. Some online sources include Chebby, the link is listed here, and also PubChem. These last two are free to search. They don't cost anything, and they're very useful databases. Also, look up your biology as well. If you're running a biological assay, you can find information about compound classes. I generally have found that alkaloids have been common in central nervous system assays. Phenolics are common in antioxidant screens. And again, knowing the class of compound you're dealing with helps to suggest some purification strategies. Again, research journals are very good for that, as well as any internal databases you might have at your institution. I'm going to talk about columns that I have found useful for screening. They can be divided up into three types: normal phase, which includes silica, alumina, and diol; reverse phase, which is C18; and ion exchangers, such as the anion exchange and cation exchange columns. These different columns give different compound selectivity or elution order, and all of these columns are very suitable for wide polarity range chromatography, which we shall discuss next. Wide polarity range chromatography uses a range of miscible solvents to elute compounds off of a column. We always start off with a weak solvent and use a succession of stronger solvents to elute the compounds. What do I mean by weak and strong solvents? Well, a strong solvent is a solvent that elutes the compound off of the column very easily. A weak solvent tends not to elute compounds. A strong solvent and a weak solvent mean different things in normal phase and reverse phase. For example, water is a very strong solvent in normal phase chromatography, but it is a very weak solvent in reverse phase. Wide polarity range chromatography allows you to obtain an approximation of the compound polarity based on the combination of solvents that elute the compound. wide polarity range provides the best opportunity to elute unknown compounds, which is what we have to deal with in natural products. And then by polarity range, it also suggests other solvents as well. Schneider and Kirkland, in their book, Introduction to Liquid Chromatography, have this diagram. This diagram can also be found in our flash chromatography guide, and I'll give you information on how to obtain this free guide at the end of the seminar. But in here, the polarity of the compound is in parentheses over here, and you notice that the compounds are separated into different groups, or rather the solvents are in different groups. The reason for these groups is that the solvents in a particular group tend to elute compounds the same way with the same order. If I have a solution, or if I'm trying to elute a compound and I find that ethanol, for example, fails to separate my compound from impurities, using one of the other alcohols in this group 2 over here probably won't improve the chromatography, but using another group such as tetrahydrofuran might work better. The general method for wide polarity range chromatography is I'm going from weak to strong solvent. I'm using the automatic solvent switching that's built into the CombiFlash system. And very important is I'm using miscible solvents. So in this case, I start off with hexane and go to isopropanol. Then from isopropanol, I run a gradient to water. Isopropanol is stronger than hexane, it's weaker than water, and it's miscible with both solvents, so I don't have miscibility problems. This is green tea extract, and in this case, chlorophyll eluted over here. This broad peak here was a mixture of alkaloids and phenolic compounds, and what appeared to be tannins eluted as I started to go into the aqueous gradient. As an example for wide polarity range chromatography and also for column screening, we're going to use capsaicin. We used a extract from green chili peppers, and during these runs we used a variety of detection techniques all at the same time, including UV, all wavelength collection, evaporative light scattering detectors, and the pure ion mass spectrometer detector. Each experiment used about 3/4 gram of extract on a 12-gram column, and I used solid load cartridges. The reason for this is the extract has as we all know, a wide mixture of compounds. I used a solvent to dissolve the compounds, or a mixture of solvents to dissolve this mixture of compounds, but this solvent mixture is also very strong chromatographically speaking, so if I just did a liquid injection, the compounds would not stay on the column, they would just run right through the column without any interaction at all. So the solid load cartridges improved the chromatography greatly. In the first example, we used normal phase wide polarity range chromatography. The gradient was hexanes to ethyl acetate to methanol, and then methanol to water. The solid load cartridge used was, again, I absorbed the sample onto silica in this case because I'm running a silica column. Detection was at 254 nanometers, the ELSD, and the pure ion mass spectrometer. And even though I'm running a very, very crude mixture, you can see that I'm getting some very, very clean mass spectra out of here, despite a number of peaks eluting next to each other. The second peak that I have as a spectrum shows a mass of about 950 Daltons. I found the capsaicins eluting much earlier, and they showed up pretty nicely in the mass spectrometer as well. Even though I have a nice clean mass spectrum, I can also see that I have some impurities that eluted as well. I also ran diol as a normal phase column, ReadySep RF gold diol. In this example, I failed to find capsaicin in any of these peaks, so it either failed to elute or more likely it eluted as a very broad peak that was very weak. The gradient here was hexane to 2-propanol, then up to water. The reason why I like to use diol is it is often less retentive than silica. Even though I have a mixture of peaks that eluted in the hexane propanol gradient, I'm still getting some nice clean mass spectra, including something at almost 2,000 Daltons in this case. The other normal phase column that I ran was alumina. I used the same gradient as I did with silica. Speaking of these gradients, when I'm running these very polar solvent systems, such as methanol, water on silica, one thing very important is not to use basic solutions such as ammonium hydroxide, since ammonium hydroxide in very polar solvent systems will dissolve your silica. The reason why I ran alumina is it does have a different selectivity as compared to the other columns. You can see that the chromatogram looks very different than the previous slides. In this case, the capsaicin compounds eluted as a single peak, although I could see several capsaicin compounds in the mass spectrum. I also see some impurities over here, but in general, the capsaicins eluted more cleanly than in the other normal phases. So by using a variety of columns, I was able to find a column that allowed my compound to elute more cleanly. I ran reverse phase wide polarity range chromatography, and in this case, the gradient was water to methanol, and then methanol to 100% dichloromethane. The second part of this is non-aqueous phase, reverse phase. The capsaicin compounds, I could resolve capsaicin compounds from each other, but you could still see from the general chromatogram that they weren't resolved very cleanly. But the fact that I could see them resolved from each other suggests a possible secondary purification step later on. So, what did we learn from this example? The cleanest purification of the capsaicin class came from alumina. However, the C18 was able to resolve the individual capsaicin compounds. The other thing I noted in all of my runs was that capsaicin was detected as the sodium adduct in the mass spectrum. So when you go back and look at your list of compounds that have been isolated earlier, remember to consider possible adducts such as sodium or potassium, or maybe solvent adducts as well. You might have to subtract those off to see if your compound falls into those masses. Also consider the possibility of fragmentation. For example, steroids will tend to lose water very easily, so you might see a very nice peak that's 18 Daltons off from what you expect. Also, the column screening allows a correlation of activity and compound mass. So if you're seeing that your biological activity always occurs with a compound for a certain mass, that's a pretty good indication you're starting to get some information to identify your compound. So putting it together into a single purification, the capsaicin peak from the alumina was run on C18 as an orthogonal purification method. What I mean by this is that the alumina was a normal phase column. I like to switch between normal phase and reverse phase because they allow very different selectivity from each other. The other thing is that when we ran the C18 experiment, we saw that the compounds could be resolved, but they eluted pretty late in the water methanol gradient. So what I did was I raised the starting point so that we were starting with a higher percentage of methanol so that the peaks come out a little faster, and maybe by flattening the gradient we'll get a little more resolution. The other thing is that the active compound was known to elute in the methanol water gradient, so there was no need for the non-aqueous reverse phase portion of the gradient. Also, because we're coming off of the alumina column, the mixture is somewhat clean as compared to the crude extract. So the final purification is shown over here. What I have over here is 3 peaks that eluted pretty cleanly, and the mass spectrometer, the pure ion, allowed me to identify capsaicin, dihydrocapsaicin, and homodihydrocapsaicin very easily from the mass spectra. We loaded about 30 milligrams of extra of the aluminum oxide peak on here, and we got a fair portion of that back. About 25 milligrams of that material was recovered in these 3 peaks. So the C18 column screening earlier suggested the second purification step. Another part of your column screening should include ion exchange columns, and we're going to give you some hints for working with those. The ion exchange general method is changing the ionic strength, changing the pH, and changing the ions, especially on the strong cation exchange. And so because we're changing the ions, this kind of falls sort of under wide polarity range chromatography. One important thing is to condition the column first and then get the compound ionized. Because the compound has to be ionized, you have to do a liquid load for these columns, not a solid load. The strong cation exchange is very good for alkaloids and basic compounds. This was green tea extract. 200 milligrams of extract was dissolved in 20 mils of methanol, to which I added 5% glacial acetic acid to ionize the alkaloids. When I ran the column, I first did a water wash up to about 10 column volumes. This washed off anything that was neutral and anything that was acidic. Other alkaloids are either displaced by ammonium ions, or because we are increasing the pH, they elute as free bases. So by increasing the pH, I'm causing these alkaloids to not interact with the ion exchange column anymore and causing them to elute. I really don't care about the mechanism for their elution. I'm really caring about getting the compounds pure so I could do something else with them. The other ion exchange column is the strong cation exchanger, and these are good for phenolics and other acids. In this case, I find I just need to run a single gradient as opposed to all of the other methods that we've seen earlier today. When we ship a column, the counter ion on the column is chloride, and I find that if the compound is in the chloride form, compounds don't really bind to the column very well, so I wash the column first with acetic acid to put the column in the acetate form. After I did that, I took 10 grams of green tea extract dissolved in 100 mils of methanol. I used 3% ammonium hydroxide to ionize the phenolic compounds. I then used a simple load pump to load onto a 17-gram SAX column, which I then washed with water and collected all of the alkaloids and neutral compounds. I then ran a gradient and eluted with a acetic acid gradient. Either by the law of mass action, I'm exchanging my compound with acetic acid with the acetate ion, or by making the solution more acidic, I'm eluting as the free acid. I'm able to then elute off my phenolic compounds. This mixture was then run on a Cephedex LX20 column I used a column adapter to hook up the Cephadex column to my Combi Flash. I was able then to use my fraction collector and my UV detector to cut the peaks. This hot cut, indicated by the blue area, was then run on the ReadySep RF Gold C18AQ column, and I was able to obtain pure epigallocatechin gallate and epicatechin gallate as pure compounds, and they were identified with my pure ion system and also confirmed with the literature by proton NMR. So in just a very few steps, I'm able to purify compounds very easily. In conclusion, the column screening allows determination of the best initial purification conditions. Column screening can be used to suggest follow-up purification strategies, and wide polarity range chromatography allows for complete elution of unknown compounds. Please note that especially with silica, you might have some compounds that are unretained, but wide polarity range chromatography reduces the incidence of retained compounds and allows the best opportunity of seeing everything that is in your extract and determining where your activity elutes. This is run on the CombiFlash RF system. One thing to note is once you find a method for your initial purification, you can go to a very large scale with the CombiFlash RF Torrent. Also, most of these techniques and information about our columns is available in our flash guide, Guidelines and Tactics for Flash Chromatography. We have a URL up over here that tells you how you can get this free flash guide. My contact information is up here if you have any questions later, and stay tuned for upcoming flash chromatography webinar topics. I thank you for your time with us, and we'll open it up now to any questions.
Okay, we'll give you just a few minutes to submit some questions here. Jack, first question I have coming in here is many of your examples used the pure ion system to help analyze. Is that absolutely required for all natural products, or will a combo flash unit or a flash chromatography unit work by itself?
A flash chromatography unit will work by itself, although the pure ion does make it easier to find the known compounds as they elute. But you can still use the wide polarity range chromatography technique on most flash systems. And you can still collect the fractions by UV or other methods. You can then analyze the mass spectra if you need offline. How expensive is the mass spec attachment for a current RF system, or is it something that needs to be bought with a new unit? You can upgrade an existing RF200 or later system. The upgrade cost on the order of about $70,000, and it's pretty easy to upgrade an older system as well.
Okay, the next question that we have coming in is that during the presentation you mentioned several different types of columns. Do you have a favorite type of column that you like to use for this type of synthesis, or?
I don't have a favorite. The reason why I do the screening is it lets me determine what is the best column. Please note that some of the columns are reusable. The ion exchange columns are reusable, and you can use them many times if one takes a little bit of care of them. Likewise, the C18 and diol columns are also reusable. I find that the alumina and the silica columns, they do tend to have a little bit more unretained material on those, despite the use of wide polarity range chromatography. So for those columns, I tend to use them one time, but they're also relatively inexpensive compared to the other columns too.